Welcome to this lecture series in linear algebra. In this lecture, what we will learn is the second isomorphism theorem, and all we need to know is the first isomorphism theorem. So what it says is that if we have a linear map from a vector space V to a vector space W, then it factors through the quotient coming from the kernel of the linear map, and the new map that we get is an injective linear map. This is the natural projection. We saw a more general version of this, but we don't need to know for this lecture the more general version. All right. Here are some problems for practice. And now let us quickly prove the second isomorphism theorem. So fix two subspaces U and W of some vector space V. Then the theorem states that this quotient, which is a legitimate quotient because this is a vector space containing W. So this quotient is isomorphic to this quotient. Note that both these quotients are meaningful. This is a subspace of that, and hence this quotient makes sense, and this is a subset of that, hence this quotient makes sense. And we say that, we are claiming that these two quotients are isomorphic. Well, two finite dimensional vector spaces are isomorphic if and only if their dimension is the same. So as written, this theorem is not saying much. It's just saying that the dimension of these two things are equal, which is saying something, but the proof will illuminate much more than what is written. So what is important is how they are isomorphic, not just that they are isomorphic. And in fact, what is important is how we prove it, not in fact the exact isomorphism that we will construct. The methodology of the proof is what I really want to stress upon. Having said that, this is a very useful statement nonetheless. All right, so here is the proof. It's a very short proof. First, we have this map, which is the inclusion map. So this map just takes a vector little u and maps it to little u. This is, of course, a linear map. All right, then we have this natural projection map onto this quotient. Okay, and recall what this does is take some vector x and output x plus w. That's that map. This composition, the composition of these two maps is what we will be calling T. So this is T. And we can just see that takes little u to this particular coset, this particular vector. This is a vector here. Okay, so that's the description of capital T. Now let's figure out the kernel of T. What is the kernel of T? Kernel of T is those things in U for which Tu is well. Okay. Tu is the zero of. Tu is the additive identity of this guy, which I will write like this, where this 0 is the additive identity of this guy. Okay? But since we know the description of T, this is same as asking, when does this happen? Which is same as those things in U, such that U belongs to W. Right? Which is same as capital U intersection W, because it just reads those things in U which are also in W. So that's precisely the intersection of U and W. And now by first isomorphism theorem, this factors injectively through the quotient by the kernel. The kernel we just calculated is U intersection W. So we get some injective linear map T bar, where of course this is also the natural projection. By abuse of notation, this will also be denoted by pi. So this takes little u to this particular coset. Okay. Now T bar is injective. We claim that T bar is also surjective. And that will follow if we can show that this is surjective. Once this is surjective, this is automatically surjective. This is a purely set theoretic fact. If you factor out a surjective map, then this guy will be surjective. So why is this surjective? Well, pick something here. An arbitrary element of this guy will look like this, which is nothing but that, because the little w kind of gets absorbed here. So this is equal to that, and hence this guy is in the image of t because this guy is in the image of t. Just take the image of little u under t, you will get this guy and hence this guy. So this is surjective. This is surjective and hence t bar is surjective, but then t bar is both surjective and injective and hence bijective. So we have a linear isomorphism between u mod u intersection w and u plus w mod w, and therefore these two spaces are isomorphic. So this diagram is the proof. Okay? And this way of reasoning, this way of doing things is what I want to really impress upon the reader or the viewer. Not just the bare fact, even though ultimately for this lecture all we'll use is this fact. So here is a corollary, which was stated as an exercise earlier, I think. So if u and w are subspaces of a vector space V, again everything is finite dimensional, then the dimension of the sum of the two spaces is the sum of the dimensions minus a correction term, and you can compare it with the set theoretic identity. If we have two finite sets A and B, then their union, not plus, the union of A and B has this cardinality. So what is the reason? The reason is we have, as we just saw, this space is isomorphic to that space. Therefore, their dimensions are equal. And now use the fact that the dimension of the quotient is the difference of dimensions. And now rearrange. If you take this to the other side, you will get that equation. So that finishes the proof. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.